Now I'm going to show you a few properties of the discrete Fourier transform in 2D. This is the equation that computes the Fourier transform. As we have seen in the previous video, I have a sum for the coordinates x and y, so in the two directions of the image, and then I'm going to compute what matches between the function f of x and y and an exponential that is computed also considering the two coordinates x and y, and computed also by considering a pair of frequencies u and v, which are also defined in terms of directions of these frequencies. So in this case, in the 2D case, x and y are coordinates of the image, and u and v are frequencies in each direction. As in the 1D case, you have to evaluate it for a range of u and v, and u goes from 0 to n minus 1 and v goes from 0 to m minus 1. We also have the inverse discrete Fourier transform, which allows us to reconstruct the image from the transform. So the transformed version is this capital F of u and v, and the change here in the formula, it's very much the same formula, but instead of having as input the image, it has as input the Fourier transform of the image, and this signal of the exponential is inverted now. So it was minus and now is plus. And with that we can reconstruct the image from its transform. And this, in the same way, we have to compute this equation for every pair of x and y. The Fourier transform has some interesting properties that I'm going to show now. We can write the DFT 2D in a polar form. So I have the magnitude of the vectors related to the complex cosine and sine, and also the phase. And I'm going to be able to reconstruct that by taking the average the real part squared plus the imaginary part squared, and then the square root of that. So basically I'm getting the Euclidean norm of this vector, and this we call the Fourier spectrum. And the phase angle is defined by the imaginary part, so every point of u and v for the imaginary part divided by the real part, and we get the arctangent of that ratio. Then we have this will give us the angle that defines the difference between the sine and the cosine, how they differ with respect to each other. So for example, if we have some the same value here in both numerator and denominator, we're going to have a value of 1, and then different values depending on the ratio of those two. Another very common representation is to use what we call the power spectrum, which the spectrum with squared, and then with the power of 2 we call that the power spectrum. We talked about the property of the first element of the Fourier transform. This happens in the 1D and also in the 2D case. When we set both frequencies to 0, the exponential becomes 1, and then what we have basically is a kind of a mean or an average value of all pixels of the image. So it's proportional to the sum of all values. In this case, it's normalized by 1 over the square root of n times m, but it is related to the sum. And another interesting property is that the Fourier spectrum of a real function is even. That means it is symmetric with respect to the origin. We saw that in practice because we plotted a version of the 1D Fourier transform, and we saw that the shape of the magnitude has this mirror effect. So the beginning looks like the end of it, but flipped. And the phase is odd, so anti-symmetric in this way here. It is useful to reposition the quadrants of the FFT by using a displacement that is called FFT shift. This can be carried out by using the coordinates -1 to the power of x plus y. I'm going to show you in the notebook. So in the previous video we visualized the spectrum of those two images here. One image is a noisy image and the other has like a smooth transition. And when we visualize that, we note that there is a dot here on the corner that has the largest value. In this case, I'm computing and plotting the power spectrum, which is the magnitude squared of each Fourier transforms from images 1 and 2. And as we can see here, there are two problems. First, that the lowest frequencies are on the corner of the representation, and those lower values are very important, and we want to look at those values, at those low frequency values. It would be much better if they were centralized. And also the power spectrum hides values that are very small compared to the value related to the first coefficient of the Fourier transform, because it is is proportional to the sum of all values. It tends to be much larger than the other ones. So in order to diminish this effect, we are going to use two techniques. The first is use the logarithm of the magnitude, which will give much less weight to the maximum value. And also we are going to include the FFT shift displacement. For our convenience, this comes already implemented in the NumPy package, so we can just use np.fft.fft shift, and then that's it. So after computing the FFT shift, the central part of the Fourier spectrum become related to the lower frequencies. And as I go far from the center, this includes the higher frequencies. So as you can see here, in a noisy image, we have frequencies spread all over the values of U and V. While in the right hand side here, because it's a much more well-behaved image, it's indicating in this Fourier spectrum that we have a value that is changing, or the frequencies change is lower from the middle, which are related to the lower frequencies, to far from the middle, which are points related to higher frequencies. So in here, I'm just showing you one magnitude of a given image, and in the original version it has values or larger values on the corners of the image. By computing the shift, then we centralize the values, and it's much easier to see the patterns. And by computing the logarithm, we can also see other frequency patterns that are present in the image. Don't forget to include 1, because to sum 1 to avoid log of 0. Another property of the Fourier transform is that it is invariant to translation. So for example, in here I have this image, and the Fourier transform of this image here is on the bottom side, Actually, what I'm plotting here is the spectrum, and by using FFT shift. But if I compute the same DFT for this image, it is actually the same in terms of the magnitude, because the ways the pixels change along X and Y are exactly the same. They are just shifted. And because in the Fourier transform what we do is to sum the values, so the sum becomes the same after all. And the Fourier transform is covariant to rotation. So as we rotate a given object that is present in the image, the Fourier transform would have the same spectrum but also rotated. Note that the frequencies are along the axis that include the largest transition values. So in here, because this object defines a line, so in this direction here we have a lot of white values, and then when we cover this diagonal here, it changes from black to white, and then to white, from white to black, black to white, and white to black, and so on. So in this direction there is a lot of transitions, and that's why it works like that. The magnitude appears like that. And if I compute, for example, the Fourier transform of this image here, this is basically the same of those two previous, the two first ones. Why is that? Because basically what I did was actually a translation. I just got the same object and then splitted it in two parts, so the frequencies, so the variations considering the pixels are exactly the same. So after the FFT shift, as I told you, in the central part of the image we're going to have lower frequencies. So those are the coefficients related to lower frequencies with respect to U and V, while higher frequencies are further from the center. So if you observe an image that has noise, it will, after the FFT shift, have information on the higher frequency side, while more smooth images will concentrate its frequencies on the central part after the FFT shift.